What happens when you measure a qubit? Imagine holding a tiny spinning coin that can be both heads and tails at the same time. That's similar to what a qubit does before you look at it. When you measure a qubit, something fascinating happens. Its quantum state, which might be a mix of both 0 and 1, suddenly chooses 1. This process is called collapse. Before measurement, the qubit exists in a superposition, meaning it has complex probability amplitudes, often called alpha and beta, for being 0 or 1. The chance of finding it as 0 is the square of the magnitude of alpha, and for 1, it's the square of beta. These two probabilities always add up to 1. When you measure, the qubit instantly becomes either 0 or 1, and the superposition disappears. The moment you observe it, the quantum state collapses into a definite classical state. This collapse is irreversible, meaning you can't get back the original superposition once you've measured. The measurement usually happens in the computational basis, which is just the standard way of looking at the states 0 and 1. Physically, this involves an interaction between the qubit's physical system, like an atom or superconducting circuit, and a measurement device that reads out the information. There are different types of measurements. Final measurements happen at the end of a quantum algorithm to read out the result. Mid-circuit measurements occur during the process and can influence future steps. Partial measurements only look at some of the qubits, which is useful for fixing errors without disturbing the whole system. Multi-qubit measurements involve checking multiple qubits at once, often used in protocols like quantum teleportation. Measurement is also key in measurement-based quantum computing, where the entire process depends on a sequence of single qubit measurements on an entangled state. In real quantum computers, this process involves converting quantum information into classical bits through specialized hardware and software. To sum up, measuring a qubit turns its quantum state into a classical bit, revealing whether it was a 0 or a 1. This act of measurement is essential for reading results from quantum calculations and is a fundamental part of how quantum information is processed.